Hubble has now been in space for over 33 years, and his mission has been a resounding success. It was never designed to look at objects in our solar system, but that hasn't stopped it from actually doing so over the course of its mission. As a result, it has captured some very special moments we would have otherwise missed. Not every planet has its own dedicated mission, and there is a lot to see besides just planets in our solar system. So, let's take a journey through our solar system, from here to the very outer reaches, looking at some objects you probably never even heard of as we explore what exactly Hubble has seen in our cosmic back garden. I'm Alex Molan, and you're watching Astronomy. In this episode of the Hubble Images series, we'll look at some Hubble snapshots of our solar system, and I'll give you a context and an explanation of the special moments it's captured. Let's begin our grand tour of our solar system right in our own backyard with our immediate neighbor, the Moon. Now, the Moon has a very big apparent diameter in our sky, which means Hubble can't fit the whole thing in one go. Also, there are other missions out there which capture far better images of the Moon, like NASA's Lunar Reconnaissance Orbiter, for instance. So, Hubble's time is better spent looking elsewhere. However, this image was taken in 2012, just as Venus was passing in front of the Sun. So, why image the Moon? Scientists are using the Moon as a giant mirror to search for slight variations caused by sunlight being scattered through Venus's atmosphere. These variations allow scientists to determine the chemical composition of the atmosphere. Now, we already know the composition of Venus's atmosphere, which means this was just a test to see if the light-scattering experiment produces accurate results. You see, Hubble often looks at distant stars when an exoplanet is transiting in front of it, and it uses this process to determine the composition of that exoplanet's atmosphere. The Sun is too bright for Hubble to look at directly, so light reflected off the Moon provides the results scientists were looking for. Hubble might struggle to fit the Moon in one go, but this is less of a problem for our next planet, Mars. Mars is often imaged by Hubble, giving us a full view of the entire disk, which can't always be seen by orbiting spacecraft. In these images, Hubble can spot dust storms, seasonal variations, and other weather phenomena, important information to have for any rovers on the surface and to build up a catalog of information which can be used to better predict the weather in the future. This time-lapse shows a planet-wide dust storm obscuring most of the surface features from view. However, you'll also notice Mars's two moons, Phobos and Deimos, whizzing around the planet in the background, and they really are whizzing. Look how far they travel in just 42 minutes. This time-lapse shows another view of Phobos, Mars's closest and largest moon, moving over the course of 22 minutes. Phobos orbits the entire planet in only 7.5 hours, meaning it is the only moon in the solar system to orbit quicker than a day on the parent planet. Stepping past the last of the inner planets before we arrive at the first of the gas giants, there is a barrier to cross, the asteroid belt. Still, this region is filled with fascinating objects for Hubble to study, such as the misleading asteroid 6478G. It may surprise you to hear that this is an asteroid when it clearly looks like a comet. It's even got two tails, like we are used to seeing on a comet. But no, this is, in fact, an asteroid found in the asteroid belt and imaged in 2019. So, what's with the tail? Well, it is believed that this 3.5-kilometer-wide asteroid has been steadily speeding up its rotation due to something called the YORP effect. Radiation from the Sun has a slight pushing effect, meaning when it acts on an irregularly shaped body under the right conditions, it can cause the body to speed up its rotation. Asteroid GS rotation has gradually sped up until it now rotates once every 2 hours, right on the limit of what an asteroid can handle. Loose matter is being ejected into space by centrifugal forces, which are now overcoming the gravity of the asteroid. Eventually, this asteroid will disintegrate altogether, as most asteroids and comets are not solid rocks but more like rubble piles. With somewhere between 1 and 2 million asteroids larger than a kilometer in this region, and millions of smaller ones, the asteroid belt is a chaotic place. To show you what I mean, let's examine P2010A2. This looks like a pretty standard comet. Wouldn't you agree? Having a Close-up look at the nucleus. Though, what is this weird filamentary structure? Surprisingly, this isn't the shape of the comet's nucleus. Again, this isn't even a comet. What you're looking at here is an extremely rare event, two asteroids gliding. This X shape near the nucleus is, in fact, streamers from the impact rubble being flung into space in four directions, slowly being pulled back in towards the center of mass by the extremely weak gravity, with particles in the tail here having escaped the gravity well altogether. Beyond this small chaos, asteroids in the belt remain in fairly stable circular orbits around the Sun. If they were to stray from this path, as comets do, they would start having to worry about a much larger source of gravity, Jupiter. Jupiter is sometimes referred to as the solar system's vacuum cleaner, and for good reason too. Jupiter, by itself, is so massive it makes up almost 3/4 of all the mass in the solar system, excluding the Sun. As a result, it has a powerful gravitational effect on nearby objects. This was particularly evident when the 2 kilometers wide comet Shoemaker-Levy passed too close to the gas giant in 1994. Jupiter's gravity not only pulled the comet in, it also ripped it apart, meaning by the time Shoemaker-Levy impacted Jupiter, it was already in several different fragments. This was the first direct observation of an extraterrestrial collision. Interestingly, Shoemaker-Levy had been captured by Jupiter around 20 years previously, but up until this point, it was orbiting Jupiter as an active comet. Again, the first time this had been observed. However, this orbit took it too close to Jupiter's surface, where tidal forces pulled it apart, and only a year later, these fragments impacted Jupiter at 60 kilometers per second, or 210,000 kilometers per hour. The impacts caused fireballs over 23,000 degrees Celsius, which rose 3,000 kilometers above the limb of the planet. The largest impact left a dark spot on Jupiter over 12,000 kilometers across, about the size of Earth, and the impact was estimated to have released energy equivalent to 6 million megatons of TNT, or over 600 times the world's entire nuclear arsenal put together. Various impacts, while perhaps not as impressive, have been imaged since and give weight to the theory of Jupiter being a cosmic vacuum cleaner, protecting the inner solar system planets from devastating collisions. Beyond its destructively powerful gravity, Jupiter has other sides for Hubble to see that are a little more on the ethereal side. You see, Earth isn't the only planet to experience auroras. While you can see auroras with your naked eye on Earth, auroras are actually brightest in the ultraviolet. As I mentioned before, Hubble can detect ultraviolet light, meaning we can closely observe this phenomenon on other planets too. Jupiter's is the easiest to spot. It's the biggest and closest of our neighboring gas giants, and its powerful magnetic field and strong radiation produce a bright aurora. In 2016, the Juno spacecraft was on its way to Jupiter, which provided scientists with a unique opportunity to measure solar wind on its way to Jupiter with the Juno spacecraft and observe subsequent changes in the aurora with Hubble. As a result, Hubble observed Jupiter almost every day for several months. What Hubble found out was that these auroras are hundreds of times more powerful than on Earth, with a radiant power of 100 terawatts, but also surprisingly, they never cease. On Earth, auroras light up around the poles during a solar storm. This implies that auroras on Jupiter are not just powered by the solar wind. Since Juno has arrived at Jupiter, the data it has collected suggests that the auroras are mainly powered by charged particles in Jupiter's fierce radiation belt, which feed into the planet's atmosphere via its magnetic field lines. The magnetic field has also been found to produce alternating currents rather than direct currents. This accounts for the radiant energy of the aurora, which would be impossible if energy were transferred through the magnetic field via direct currents. We've spent a lot of time with Jupiter, but let's take the time to examine a very special one of its moons, Europa. After all, this may be the home of our closest living neighbors, and Hubble has captured images of it in surprisingly high detail considering the distances involved. For those of you that don't know, Europa is a large moon of Jupiter and is one of the most promising candidates for life in the solar system. We aren't expecting to find anything on the surface, but rather, underneath, In an ocean of liquid water, Europa is an icy world, and being this close to Jupiter produces extreme tidal flexing. The theory goes that energy produced from tidal flexing keeps the underground ocean warm enough for it to remain liquid. Various missions have since been looking for evidence of this ocean. Surprisingly, Hubble has been very useful in this endeavor. Galileo and the Voyagers were able to produce much higher resolution images of Europa compared to Hubble because they passed the Moon by reasonably closely. However, these missions were not able to observe the ultraviolet. With this ability, Hubble has spotted possible plumes of water erupting on Europa's surface. Volcanic activity would imply that the interior mantle of Europa is liquid, and because it must be water, this suggests the ocean theory is correct. Since the first observation, lots more plumes have been detected. Hubble's vision was utilized again to detect salts on Europa's surface. Most missions use infrared to examine a planet's surface, as most of the interesting emission bands of substances are found in the infrared. However, sodium chloride, or salts similar to those found in our oceans, are mainly visible in the visible light spectrum, which means these salts on the surface of Europa were undetected by Galileo. Hubble, viewing in the visible light spectrum, confirmed that sodium chloride is found all over the surface of Europa, likely having originated from the underground ocean and then carried up in the plumes to be deposited on the surface. The exciting prospect about an ocean of sea salt is that it indicates the ocean floor could be hydrothermally active. These thermal vents on Earth can be a hive of life, so scientists are excited to investigate this further. Although, sadly, we may still be a few decades from having a submarine mission to check this out. Let's continue our tour. There are other gaseous planets to explore, and for our next image, Hubble turns its gaze away from Jupiter and onto Saturn. Since Cassini ended its mission in 2017, Saturn has been without a dedicated mission. This means the best view we now have of Saturn is courtesy of the Hubble Space Telescope. Hubble is often observing Saturn, checking for various phenomena. Hubble can monitor the weather on Saturn, giving us a better understanding of seasonal variations in the atmosphere. Cassini was only around Saturn for half a Saturnine year, meaning Hubble is now filling in the remaining data as best as it can. The most notable events Hubble witnesses are huge storms, which span across thousands of kilometers on the planet. But because the Saturn system is such a beautiful place, all the data collection also provides some striking shots. Here are a few of my favorites. We're reaching the end of our tour now with just a few planets left to visit. As we've traveled out from Earth, Hubble has captured more and more distant objects, which, if it hadn't been for the Space Telescope, would have been increasingly hard to study. Now, we have finally arrived at the first of the icy giants, Uranus. Much like Jupiter and Neptune, Uranus has also had Hubble observe storms on its surface and even had aurora detected around its magnetic poles, which apparently do not line up with the rotational axis at all. Uranus's rotational axis is already pretty weird, appearing to be on its side compared to the rest of the planets in our solar system. This means that at some points in Uranus's year, it appears to roll along its orbit. It also means that it hardly ever experiences a solar eclipse from its moons. 2006 was the first opportunity we had to witness this event, as the last time the moons were aligned correctly was in 1965, before telescope technology was good enough to see a satellite transit on an object so far away. Hubble not only saw the aerial shadow crossing over Uranus's surface, but also a complete view of Uranus's bands. Since this equinox view through Hubble observations of Uranus over a section of its lengthy 84-year orbit, we've also been able to see seasonal variations develop in the atmosphere. As a pole becomes more exposed to the sun, the atmosphere seems to get lighter in color. This is believed to be a large cloud cap that forms during that hemisphere's summer, and it is expected to dissipate again as Uranus heads back towards its year's equinox. As Hubble is only 33 years old, it hasn't even been able to see half a year on Uranus, so there's still a lot to learn about its seasons. Yet, one object that we would have never even known about if it wasn't for Hubble is the smallest moon of Neptune, Hippocamp. The outer ice giants, Neptune and Uranus, have largely been forgotten by space agencies around the world, only ever having one flyby in 1989 by NASA's Voyager 2 probe. This means that our knowledge about these massive worlds is pretty limited, and it would be more limited still were it not for Hubble observing them from time to time. One of the major discoveries Hubble made about Neptune was the discovery of a new moon in 2003, which has now been named Hippocamp. Now, Hubble has discovered many moons in its time, especially around Jupiter and Saturn, but what makes Hippocamp special is that it could well be a fragment from the much larger moon of Neptune, Proteus. The 400 kilometers wide moon does indeed look like it had a tumultuous past with giant impact craters, 50 to 100 kilometers in diameter. One of these collisions likely fragmented parts of Proteus, which then fell into orbit around Neptune. Hippocamp is probably the biggest fragment as it's an irregular 35-kilometer-long object and orbits fairly closely to the larger Proteus. As our penultimate destination, let's move on to Neptune itself. As I mentioned before, Hubble was never really designed to monitor our solar system. However, in 2015, it was decided to dedicate more of Hubble's time to the outer ice giants, having roughly one observation per year. This has meant that we can better monitor seasonal changes in those planets' atmospheres. One of the most noticeable of these changes are the giant storms spanning thousands of kilometers. Voyager 2 saw one such storm as it passed Neptune back in 1989, which was later dubbed the Great Dark Spot, comparable to Jupiter's Great Red Spot. However, unlike Jupiter's storm, the one on Neptune has since disappeared altogether. Other storms have come and gone, and the latest one was seen in 2018. It lasted a few years, but it too is now believed to have disappeared. While there is not enough data to speculate on how these vortices develop, it could be that Neptune is like Jupiter with bands in the atmosphere. While they won't be as defined or as many as there are on Jupiter, the bands on Neptune would travel at different speeds. This could cause vortices to appear where the bands meet. Once the storm has got going, it can drift around the planet even between the bands, but once it leaves its power source, it begins to slowly diminish, which is what we have seen. Interestingly, Hubble is the only program that can monitor these weather changes, as in most light wavelengths, they are very, very hard to spot. Hubble, though, can probe Neptune and Uranus in the ultraviolet. By this point, you might recognize that we've run out of planets, so our tour must come to an end. But perhaps, before we conclude, there is one last dwarf planet that bears looking at beyond Neptune that has been the target of Hubble's study. I'm sure you all know it. I am, of course, referring to 2007 010 Orgonghae. Which dwarf planet did you think I meant? You would be forgiven if you have never heard of this object before, even if it is the third biggest dwarf planet in our solar system, third only to Pluto and Eris. And like them, this dwarf planet is also found billions of kilometers away in the Kuiper Belt. While this object was not discovered by Hubble, Hubble did find out that it had a moon. It was not discovered by the original investigator, as it was very faint in the images. However, recently a research team had a suspicion that 2007 010 could have a moon, as it has a slow rotation of about 45 hours. Most Kuiper Belt objects rotate in under 24 hours. It was hypothesized that the moon's gravitational tug may have slowed it down, and after searching some archival Hubble data, it proved to be so. This discovery means that nearly all the dwarf planets in the Kuiper Belt have now been found to have their own moons. This could be because, out in the Kuiper Belt, objects move pretty slowly. This means that if there ever were collisions between objects, then fragments would have stayed in orbit around the body rather than escaping the object's gravity. This could be why asteroids in the asteroid belt don't tend to have moons. Collisions there are a lot more energetic, meaning debris just boots off into space. Finding the moon around 2007 010 means that we can have better constraints on our solar system formation models, so useful data indeed. You can see from just these images how important Hubble has been to humanity's knowledge about space and our solar system, and it has done far more than just this. Over the course of the last 30 or so years, Hubble may well be the most important space mission to date, expanding our horizons and providing data that will be utilized for many years to come. And given that it might last until 2040, it might even outlive its spiritual successor, the James Webb Space Telescope, which was launched in December 2021 but is only expected to last for around a decade. Of course, the James Webb Space Telescope is eager to make up for its potentially shorter lifespan and has already started turning its gaze to some of the same planets Hubble has imaged. I can't help but be captivated by this image of Jupiter captured in the Webb's NIRCam. The fact that the Webb primarily captures light in the infrared range means that its images have an ethereal beauty all of their own. You can see here in stunning detail the haze of auroras on Jupiter's north and south poles, or, here in this image, detailed images of Jupiter's rings. Yes, it has those, as discovered by Voyager 1 in 1979. I find this image of Neptune equally entrancing, seeing how tiny it looks in the vastness of space and then realizing that this is an entire planet captured in incredible resolution really strikes home at the power that the James Webb Space Telescope brings to bear. These images have caught some of the faintest rings of Neptune that haven't been imaged in nearly 3 decades since Voyager 2 flew past. This is also the first time the rings have been seen in infrared, giving scientists much to learn about them and the stormy planet they surround. The Webb has even taken a cool image of Saturn, whose rings shine brightly against the darker planet. This is a little misleading, though methane gas in Saturn's atmosphere absorbs almost all the infrared radiation coming in from the sun, making it appear darker. Meanwhile, the icy rings are much less absorbent, making them glow as you see here. Ultimately, however, there is no contest between Hubble and the Webb, as the two are not directly competing. Given the differences in the spectrums of light they are able to detect, the Webb can't ever provide what Hubble can, a clear picture of what these planets might look like to an unaided human eye. Similarly, Hubble can't detect all the bandwidths of radiation that the Webb is able to see. They each have their niche, and they each advance our scientific understanding. I am excited for what the James Webb Space Telescope will bring, but this is definitely a good time to appreciate Hubble's accomplishments, and I look forward to what the future will bring for it too. To walk outside at night and peer into the glittering darkness of space is a special experience, but one that doesn't capture the true majesty of space and everything it contains. Light pollution, atmospheric distortion, and our limited eyesight prevent us from truly exploring the universe and discovering its secrets. Thankfully, the Hubble Space Telescope, from its position orbiting around 550 kilometers above Earth, allows us to overcome these limitations and see deep into space, changing our understanding of astrophysics and shaping our knowledge of the universe, while also dazzling us with remarkable images. I'm Alex Molan, and you're watching Astronomy. Today, we're going to look through the Hubble telescope, take a journey billions of light years into space, explore, and give context to the furthest reaches of our galaxy and far, far beyond, all the way to the most distant object ever seen. What will we see along the way, and what will Hubble surprise us with in this episode? Our first encounter is 3,800 light-years away, where we see vast blue wings stretching out into space. But what is it? This is NGC 6302, otherwise known as the Butterfly Nebula. Lying within our Milky Way galaxy, the Butterfly Nebula's spectacular array of blue and turquoise colors is actually the glowing gas that was once a star's outer layer. The wing shape showcases the expansive journey that this gas has taken over the last 2,200 years, covering a distance of over 2 light-years. Recent observations of the Butterfly Nebula have detected unprecedented levels of intricacy in the gas jets and bubbles erupting from the star at the nebula's center, all of which create rapid changes in the wing shape you're seeing now. Traveling beyond 8,000 light-years away, we find the star cluster Pismis 24. This cluster contains a combination of remarkable phenomena. First, your eye will be drawn to the core of a large emission nebula rising up and glowing. Second, you will notice the blue stars lingering in and around the nebula. These blue stars owe their blue color to their intensely hot temperature, far hotter than our own Sunday. This is due to their mass, which determines the temperature of a star, with blue stars having at least 3 times the mass of our own. These blue stars help to give Pismis 24 its signature color and texture. Their extreme ultraviolet radiation causes the gas surrounding the cluster to heat and bubble around the star in remarkable clouds, which makes probing the region extremely difficult. For a while, Pismis 24, a star in the Pismis cluster, was thought to be the most massive star ever recorded, at almost 300 solar masses. However, it is now thought to be at least 3 stars, each weighing in at almost 100 solar masses, much smaller than originally thought, but still some of the largest stars ever recorded. Pismis 24 is part of the diffuse nebula NGC 6357, a cosmic nursery. The nebula is home to many protostars, shrouded by dark gases. Protostars are the earliest stage of stellar evolution, where stars gather mass from their parent molecular cloud. Alongside these protostars are many young stars encased in expanding cocoons of gas, making the nebula feel like a living organism. Now, let's go even further, journeying 60,000 light-years away. We come across Palomar 12, with its globular cluster of stars hanging in deep space, lingering on the outskirts of the Milky Way's halo. These stars are around 30% younger than the other globular clusters in the Milky Way galaxy. What is the secret to their young age? They were abducted. Palomar 12 isn't actually from the Milky Way galaxy, but from the Sagittarius dwarf elliptical galaxy. Around 1.7 billion years ago, the Palomar 12 cluster was torn from its home galaxy by tidal interactions with the Milky Way. In fact, Palomar 12's home galaxy is currently being ripped apart by our galaxy. These tidal forces are limited to the immediate surroundings of their respective galaxies, but when they collide or pass nearby one another, the results are striking, creating strange distorted shapes or unique phenomena, as demonstrated by Palomar 12, where clusters born in one galaxy end up living in another. Our journey doesn't end here. Hubble allows us to see much further. Let's continue our voyage outwards, hopping more quickly between locations, starting with 30 million light-years distance, where Hubble allows us to see a familiar view from a new angle. This is the Sombrero Galaxy, as we see it from the side. It shows us the flat disc-like shape of most galaxies, a view we don't typically see. You might be wondering why this flat shape is the norm. After all, planets, moons, and meteors tend to be spherical. Shouldn't all galaxies be the same? The reason for the more common flat shape found in galaxies is that, as mentioned before, the universe is in constant motion, and gravitational forces caused by the black holes at the center of galaxies cause them to rotate. With the conservation of angular momentum, this leads to an outward disk shape. The Sombrero Galaxy is notable for the blinding white core at its center and the distinct lanes of cosmic dust spiraling outwards, the most pronounced of which linger at the rim, giving the galaxy its distinct sombrero shape. Continuing further, at 65 million light-years, we see the broad elliptical galaxy NGC 1052 DF2. Do you notice anything distinct? You might have spotted its particular diffuse texture. So diffuse, in fact, that distant galaxies can be seen behind it. This gives the galaxy a supernatural, almost ghostly appearance. But the most strange of all is that this galaxy is possibly missing all of its dark matter. This was the first galaxy of its kind to display such an absence. As for why, we're not truly sure. Let's go even further, this time just over 300 million light-years from Earth. This is a Coma cluster, a large gathering of more than 1,000 galaxies, all linked together by gravity. A cluster that also happens to be one of the first places where we discovered indications of dark matter in this image that you're looking at. You can see thousands of intra-cluster globular clusters. These are spherical groups of stars that are not bound to a galaxy, but to the Coma cluster itself. While this might seem far, we can travel even further. Over 9 billion light-years away is Max J 1149, aka Icarus, once the furthest star we knew of in the universe. In fact, light from Icarus takes so long to reach us that it appears to us the same way it did when the universe was 30% of its current age. To give a sense of how far away Icarus is, at the time of its capture in this image, Icarus was at least 100 times further away from the nearest star. Yet, we can travel even further to distances that seem beyond comprehension. Nicknamed Arundel, WHL 0137LS is a star in the CES cluster whose light took over 12.9 billion years to reach us. However, due to the expansion of the universe, the distance between Arundel and ourselves is now even greater, 28 billion light-years. We are just seeing it where it was almost 13 billion years ago. Arundel is suspected to be 50 to 100 times the size of our Sun, and due to its enormous mass, it is expected to explode in a supernova in a few million years. From our perspective, nicknamed Arundel after the Old English name for morning star or rising light, the name is actually a reference to J.R.R. Tolkien's character Arundel, who traveled through the sky carrying a jewel as bright as a star. Outside of its interesting name and impressive size, Arundel also has an effective surface temperature of at least 20,000 Kelvin, almost 4 times hotter than our Sun. There is also a small possibility that it is a population 3 star, which means it would contain almost no other elements besides hydrogen and helium, and it would be far brighter than your average star. We are able to see this star through an effect called gravitational lensing, where a cluster of galaxies warp light from the star around them in just the right alignment so that they act like a huge lens, allowing Hubble to see much further than it otherwise would have been able to. Things are so unbelievably far away now that even Hubble is reaching its limits. But is there anything further that we can see on our journey to the far reaches of space? Yes, there is one more object Hubble can show us, the redshift galaxy known as HD1, the earliest and most distant known object in the observable universe. Although a little more to us than a faint red dot, HD1 is actually 13.5 billion light-years away, or at least it was when the light was emitted. It is estimated to now be at a distance of 33.4 billion light-years away, with the expansion of the universe taken into account. While it lies at the very reaches of our perception, it has some telling details. Its extremely luminous ultraviolet emission suggests it could be a starburst galaxy, producing stars at an unparalleled rate. It could also be home to the enormous population 3 stars described moments ago that are far more luminous than the stars we are familiar with. However, these and any other theories are speculative due to the minimal amount of photons we are working with. All we do know for sure is that something is out there, 33.4 billion light-years away, and for now, that's the furthest thing that we can see. To get more information and perhaps even further views of the universe, we will need the James Webb Space Telescope, the most powerful infrared telescope of all. But until then, let's be thankful for the sights Hubble has shown us and the 33 billion light-year journey it has allowed us to take. And what a journey it is! With the James Webb Space Telescope nearing its launch, I felt like it would be a good idea to have another look at some of the remarkable images of its predecessor, the Hubble Space Telescope. Hubble has been in space for 30 years now and has increased our understanding of the universe drastically during this time. A type of object Hubble has observed is galaxies. As we've seen earlier in this series, galaxies come in all different shapes and sizes, with star populations ranging from millions to the trillions. They are fascinating, beautiful objects, each containing its own story of how they formed the way they did, let alone the tantalizing question about the possibility of life somewhere in them. While we have only observed the tiniest fraction of the total number of galaxies in the observable universe up close, did you know that Hubble has seen galaxies all the way through their evolution? From galaxies in the throes of starbirth or starburst to galaxies that are inert, anemic, or dying. I'm Alex Molan, and you're watching Astronomy, and today I wanted to look through the spectrum of galaxy evolution, focusing on the ghostly, beautiful remnants of galaxies that are on their way out. I hope by the end of this video, I have earned your like and subscription. When looking at a galaxy, the first indicator of the stage of its evolution is to look at its shape. It is generally believed that spiral and barred galaxies are some of the least evolved galaxies in the universe, whereas elliptical galaxies are the most evolved. That doesn't necessarily mean spiral and barred galaxies are younger, though. It's just that they take longer to evolve. Here's an example, NGC 2336. Galaxies with spirals consist of flat disks where stars mainly orbit in the same direction. One of their defining, characteristics are the arms that extend from the galaxy center. These arms can spiral out directly from the galaxy's core, or sometimes the spirals come from a bar. They consist of a concentration of stars, gas, and dust. Galaxies that have an abundance of dust are likely not as far along in the evolution process as less dusty galaxies, as this dust has yet to be turned into new stars. Should no outside influence accelerate the dust consumption, a galaxy like this may produce stars at a fairly slow but steady rate for billions of years. Yet, how do we know it's not producing stars very quickly? Well, a distinct feature about this galaxy is the lack of red H2 regions or stellar nurseries. Instead, while star formation is clearly still taking place due to all the bright blue stars you can see in this image, it will remain as a spiral galaxy for a lot longer than a galaxy bright with H2 regions like number 69, NGC 972. Wow, what a pretty galaxy! It almost looks like it's ablaze with all the activity happening around it. When a galaxy is so red, we characterize it as a star-bound galaxy. That is to say, star formation is happening at an incredible rate. These red regions are the H2 regions the previous galaxy was missing in abundance. As starburst continues, it will quickly use up the gas and dust structures you see here, converting it all to stars. Also, notice the blue glow like a halo around the galaxy. The blue hue comes from blue stars, the hottest and most massive star type. This is another indicator of rapid star formation, as these stars require huge amounts of matter to fall into them during their formation. Number 70, Messier 61, another incredible example of a starburst galaxy, is a fantastic galaxy for observation because it's angled almost exactly face-on to us. This means all the dust lanes and its red nebulae can be studied in detail. That's a lot harder to do with a galaxy that's edge-on. Looking closely at the center of the galaxy shows a neat symmetry with the dust lanes. However, the further out you zoom, the more you notice how it becomes less symmetrical. This arm seems to split into three, whereas this one retains its structure. Usually, an asymmetrical galaxy indicates that it is being perturbed in some way, either from the gravitational influence of a nearby galaxy or from an actual collision with one. In this case, M61 is actually found 50 million light-years away in the heart of the Virgo cluster, surrounded by over 1,000 galaxies. It's this outside influence that likely causes starbursts to happen and for a galaxy to accelerate its evolution, as this outside tug of gravity causes the dust clouds within the galaxy to collapse in on themselves, creating stars. Number 71, NGC 4921. All galaxies will eventually exhaust their supply of gas and dust as they get converted to stars and then neutron stars or black holes. A small percentage of gas and dust also gets consumed by the supermassive black hole believed to exist at the center of every sizable galaxy. What happens to a galaxy then? Well, NGC 4921 is a good example of a galaxy about to transition into what is known as a lenticular galaxy. However, this one still has its spiral arms visible, so it remains classified as a spiral galaxy for now. It seems that star formation and dust lanes are key elements of keeping the shape of a spiral galaxy's arms, and when this process stops and the material runs out, the arms seem to lose some of their shape and definition. The color of the galaxy also changes to a ghostly white or reddish white, as the galaxy's blue star population burns out and disappears. This is a fascinating galaxy. It is really unusual to see a spiral galaxy so devoid of color. The only colors visible really are the few remaining blue stars clinging to the dust lanes. Astronomers have described this galaxy as anemic, as star formation here must be incredibly slow. Number 72, NGC 2217. This is the first true lenticular galaxy I've shown you today. Although NGC 2217 isn't totally done with star formation just yet, notice the blue stars around the outer edge of the galaxy. However, in this instance, the dust here is almost completely exhausted, and the spiral arms have lost their definition. The bulge at the center of the galaxy has a white and reddish hue, showing that only older and less massive star types exist here. There are no blue stars visible to speak of. Number 73, PGC 10922. Here's another face-on galaxy for you. This particular lenticular galaxy is further along in its evolution. Again, most of the galaxy here is completely devoid of gas and dust, apart from towards the center. You'll also notice how any arms that once existed have been totally wound up until they are almost indistinguishable. All that's left really are old stars and a flat disk. But even the disk will eventually lose its shape as the galaxy widens and evolves into an elliptical galaxy, like what is happening with number 74, NGC 1947. With this lenticular galaxy, we can still see the wispy remnants of the spiral arms. However, the stars in this galaxy have clearly already stopped orbiting along a flat disk and now simply orbit slowly and from all directions. The very last stages of a lenticular galaxy look something like NGC 1533. There's no gas or dust noticeable. However, you can just about see the remains of a bar structure coming away from the core, indicating that this was once a barred spiral galaxy. Eventually, what you end up with is something like number 76, Messier 105. This is a true elliptical galaxy, a galaxy almost totally devoid of gas and dust. This galaxy is so anemic that only one sun-like star gets produced in a galaxy like this every 10,000 years. So, what you are left with is a vast majority of the stars found in this galaxy being older, redder star types. If we really zoom into this image, you can see the red sprinkling of stars, especially as we move away from the brightness of the galaxy's core is the last stage of a galaxy's evolution that we can observe. These stars will last for billions to trillions of years, and the universe is too young to see what happens eventually to a galaxy like this, although it is thought that they will simply become dimmer and dimmer as one by one the stars reach the end of their lives. So, there we have it, a snapshot of the evolution of galaxies. While having an almost spooky vibe to them, I really like lenticular galaxies. Their unstable nature produces some amazing patterns that you can't find in any other galaxy type. Although it is somewhat sad to think, too, that as the universe ages, spiral galaxies will become less and less common until the only galaxy type remaining are the elliptical galaxies. I'm sure we've all seen the breathtaking imagery from the Hubble Space Telescope of beautiful and multicolored nebulae. It almost seems as if a contemporary artist flicked different colors onto a canvas. But this isn't just a pretty picture. What you are seeing here are actual structures tens to thousands of light years across. But how are these images so colorful? Does it really appear like that in real life? To answer this question, let's give you some context. Nebulae may appear solid or maybe even like clouds, but that is far from reality. Nebulae are extremely diffuse gas clouds. On average, you may get about 10 to 100 particles per cubic cm. This is far less than any artificial vacuum produced on Earth. To give you a sense of how little that really is, a comparable cubic cm at sea level on Earth contains 10 quintillion particles. That's 10 to the power of 19 particles. On the other hand, if you were to have a nebula the size of Earth, it may only have a total mass of a few kilograms. Orion, perhaps the brightest nebula in our sky, is just about bright enough to be seen with the naked eye on a clear night. However, nebulae can be a lot brighter too. If the Tarantula Nebula, found in the Large Magellanic Cloud, was as close to us as the Orion Nebula is, it would even be visible during the day. But if nebulae are so sparse, how can we see them at all? It's important to remember the scales that are at play here. While nebulae are sparse, they are also massive. H2 regions, which are a specific type of nebula, are known as stellar nurseries. These massive clouds can collapse and coalesce, and when they do, they form stars. A single nebula can contain enough mass to create hundreds to thousands of stars, and it is actually these newly formed stars that light up the gas in a nebula. Solar radiation shoots away from stars within a nebula, ionizing the nebula's particles, which releases this energy at a specific light wavelength. This means H2 regions are known as something called emission nebulae because ionized atoms within are emitting their own light. The process happening in an emission nebula is comparable to what happens in a neon light, where electricity ionizes neon within the bulb, causing it to light up. However, in a nebula, It's not neon that lights up. In fact, in the Hubble images, each color shows a different ionized atom. Unfortunately, though, I can't tell you a blanket rule for colors in Hubble images. So while in this image of the Carina Nebula, reds correspond to sulfur atoms, greens to hydrogen, and blues to oxygen, in this image of the Swan Nebula, blues correspond to visible light, blues, greens to oxygen, and reds to infrared and hydrogen. That's because of the way Hubble takes its photos. Hubble is primarily a visible light telescope, but its optical range also extends into the ultraviolet and infrared. When scientists look at a nebula, they often want to see what it is made of, so they'll photograph the object using specific filters. So, say they want to see hydrogen in a nebula, they will image the nebula using a filter that lets light being emitted along 658 nanometer wavelengths through, or in other words, the emission band of hydrogen. After that, they are left with a black and white image. Then they may decide to image the nebula again, this time looking for sulfur along 672 nanometer wavelength, and then again looking for oxygen along 501 nanometer wavelengths. Scientists then assign colors to each of these different photos and combine them together to produce the colors you see here. As you browse Hubble images on their website, you can see for yourself what the colors have been assigned by looking to see what wavelengths of light were used for Hubble images of nebulae. They are pretty much always a false color. However, Hubble does also take natural color images too. The Sombrero Galaxy, for instance, had 3 different images taken in blue, red, and green, or RGB. So the colors you see here are how you would see this galaxy were it bright enough for you to see it. So, if Hubble's images of nebulae are false color, what would they really look like to us? Generally speaking, a lot more red. The European Southern Observatory also looks at a lot of the same objects Hubble does, although often using different color filters. Going back to the Carina Nebula on ESO's website, we see that the color bands are RGB, or natural light, so we know that what we are seeing here is the Carina Nebula as we would see it. Here's ESO's version of Orion, except this time with ultraviolet and hydrogen overlaid on top of natural colors. So far, we've only discussed the most famous nebula type, H2 regions or emission nebulae. However, it is worth mentioning that there are a few other types of nebulae too. You also have reflection nebulae, where the energy from stars isn't enough to ionize the nebula. Instead, it reflects or scatters the starlight, meaning these nebulae tend to have similar frequency spectrums to nearby stars, often appearing slightly bluish. You also have dark nebulae, or nebulae with no stars around them to illuminate them. These almost appear pitch black. All in all, nebulae are not as colorful as you may have initially thought, but to me, that doesn't make them any less interesting. Looking through these filters means we can understand a lot more about nebulae than we otherwise could have, and they do make for beautiful images. Space can be beautiful. You have flawless elliptical galaxies with no traces of dust bands. Blocking the view of their stunning shape, you have grand galaxies with spiral arms that wrap around the entire galaxy with a surprising level of symmetry. And then you have the AR catalog, or the Atlas of Peculiar Galaxies. These are galaxies which laugh in the face of order, galaxies that are often going through a very tumultuous time in their existence, and they are fantastic in their own right, each with a story to tell. I'm Alex Molan, and you're watching Astronomy. In this Hubble episode, we will go through some of the most peculiar galaxies that Hubble has ever seen, and I'll try and explain what it is you are looking at. Number 43, AR 116, or Messier 60. At first glance, this galaxy doesn't look so unusual. It seems like a standard elliptical galaxy, a massive galaxy which has already used up most of its dust and gas in creating stars, which gives it this smooth appearance. It can be found 57 million light-years away and has one of the biggest black holes ever discovered near its center, at roughly 4.5 billion solar masses. But this isn't particularly peculiar so far. Zooming out a bit reveals something very unusual. M60 is right next to another very different-looking spiral galaxy called NGC 4647. From our viewpoint, It looks like the galaxies should be interacting with each other, but there aren't any immediate signs of this. This is very unusual to see two galaxies so close but without any warping of their shape. As it turns out, they are not side by side, but rather one is in front of the other. There's one other really unique thing in this image, another galaxy you probably haven't noticed. This tiny little galaxy here is known as M60UCCD1. It is the most densely packed galaxy that we know of, being only 300 light-years across but pretty much just one giant nebula. This galaxy is almost the total opposite of an elliptical galaxy, as it is rich in gas and dust that does not yet form stars. NGC 1569 is found near the MAF group of galaxies, and due to its close proximity to these much bigger companions, the gas and dust within it has recently been compressed, causing rapid starbursts at a rate 100 times faster than any observed in our own Milky Way. Towards the center are densely packed massive stars, which have blasted away the red dust and gas towards the outskirts of the galaxy through solar wind and supernova explosions, leaving behind huge star clusters. The small white stars found in the halo of the galaxy are older stars, which have been around for much longer. We can have such a detailed look at this galaxy because, although it is small, no bigger than 6,000 light-years across, it is also reasonably close to us at only 11 million light-years away. Number 48, AR-272. We'll finish with one more galaxy merger scene from a rather interesting angle. These two galaxies are roughly the same size and are just astronomical moments away from impacting each other. There's also a third galaxy found just above them, which is also in on the action. The reason for seeing three galaxies merging at the same time could be due to the fact this is happening in the Hercules supercluster, roughly 500 million light-years away, which is one of the biggest filamentary structures of galaxies that we know about in the universe. You see, the observable universe, as far as we can tell, kind of looks like a giant web, where galaxies band together to form these filaments, which form the boundaries between large voids in the universe. This is what the universe up to 500 million light-years from us looks like, and even in this space, you can see this banding of galaxies. And just because some of you have asked about this in the past, this is where Borty's void is, which is one of the biggest voids of galaxies that we know about. Thanks for watching. Making this video required some long-term planning and work, which we were only able to do thanks to the consistency and sustainability of your memberships as astronauts on Patreon. A huge thank you to everyone who has signed up, and if you'd like us to make more videos like this, you can join with the link down below. When you join, you will be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Once again, a huge thank you from myself and the whole Astrum team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.